So after we cover the uh, general transport equation and the divergence theorem, uh, now we can start talking about the finite volume method. At the beginning of the course, we talked about the different discretization technique. We talked about finite difference, finite volume, and finite element. And the purpose of the discretization technique is simply transform the differential equation into algebraic equation so you can solve that numerically instead of analytical solution. So in this case, if we are dealing with the control volume method, we would like to transport or transform the transport equation, the conservation laws, into algebraic equation. And that was originally the motivation why we have to develop the transport equation, the general transport equation. Partial rho phi by partial t plus nabla dot rho v times phi equal to nabla dot kappa nabla phi plus the source term. So this is the general transport equation. So all what we need to do is to convert that equation into algebraic equation. So we would like to convert this equation actually into a system of linear equations. We have seen many times when we went through examples how the differential equation was get into a system of linear equation when we use the different finite difference method here. So if you recall back the major steps of CFD work, you have to define your model. Now our model is actually the general transport equation. This is our model right now. Then you need to create the mesh or the grid, right? Meshing or gridding your domain, right? To be able to discretize that model into a system of linear equation. And the meshing or gridding in the control volume method is simply, as it's obvious from the name, the control volume is just a simple volume, right? So you're going to have a volume, three-dimensional element. That's my element. And I'm expecting I will have a neighboring element. So I will have another volume here. I may have one down there. I will have another one up here. I may have another one in here. So that's how the control volume works, is to have a three-dimensional element here. And we call that the cell. Each one of these elements is called the cell. And each cell has a center point. Cell, center. And we usually give that P. Then for each element, we will have east element, we will have a west element, we will have a north element, and we will have a south element. So each target cell or a volume or a control volume will have cells that's presenting the east, the west, the north, and the south. That's what we usually call it. So after you do the meshing or grading, you divide your domain into the control volumes. You determine the central or the cell center for each one of these volumes, because the approach to do the discretization is to simply, if I call that step 1 and step 2, step 3 is to integration. We integrate Yeah, we integrate the general transport equation. Let's call this the general transport equation, just for simplicity when we write it down next time. So when we integrate the general transport equation, we will able to convert that equation into a system of linear equation by the help of that meshing or gridding domain. As you see here, we are not dealing anymore with the grid itself. We are dealing with the center point of the cell. So the finite volume method, when you integrate the general transport equation, it will give you an average value of whatever the variable that you're looking for, velocity, temperature, pressure, whatever. So it will give you an average value of the volume element at the center point. So now we no longer deal with the faces of that element. You remember in that two-dimension domain, if we do meshing or gridding, right? In the finite difference method, these were the nodes that we always deal with. And you realize that these nodes now is located at the boundary of each cell, right? In the finite volume method, we will not deal with the mesh faces or mesh boundaries, but the calculation will be carried into the center point of each one of these cells. And that's the major difference between the finite difference method and finite volume methods. We are dealing with the center point of each cell all the time. So how are we going to integrate that transport equation? That's easy. We're going to do, let me write down the equation again. So the general transport equation is partial rho phi by partial t plus nabla dot rho v times phi equal to nabla dot kappa nabla phi plus s phi. So what I'm going to do, I'm going to integrate each one of these equations or these terms over the volume of the control volume. But instead of writing triple integral, I'm going to integrate over the control volume or the cell volume. Okay? And to do that, you're going to integrate that dv, 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 and dv. Now, we are doing an integration over a control volume, so we have to recall the benefits of getting the divergence theorem. That's why we explained that part, which indicating that the integration over the surface, right, of any vector field A, the normal component of that vector field over the surface of that control volume should equal the same as the integration over the volume of the nabla of that vector A, right, dv. So this is the general transport equation. Now we are integrating it, and this is the Gauss divergence theorem equation. Because now, remember, this is actually simply nabla dot A, right? That's yeah, that's the it should be nabla dot A to give you scalar at the end. So we gotta start using that the Gauss divergence theorem, because we have a few terms in here, right? That's integration over the volume, and they have vector quantity multiplied by the gradient, right? So it's highly potential that we're gonna actually replace this by the integration of the surface and vice versa here. So I can rewrite that transport equation as the integration over the control volume of partial rho phi by partial t dv plus, now I can take that term here and replace it by the integration over the surface of, now what is your vector? This is my vector now, right? This is nabla dot A, this is my A here. So this will be actually simply the rho v phi dot n. Now ds, I'm going to call that dA, which is the surface area of the control volume. It's equal to, same I can do here, nabla dot vector field, that's my vector field, can be calculated by the integration over, you can call that S or call that over the surface area, right? This is over the surface or the surface area. For this is my vector here, so this will be actually kappa nabla phi dot n dA plus the integration over the control volume of the source term dV. Again, this is my transient term in the integral form. This is the convection term. This is the diffusion term. And this is the source term. So if I want to write in words the definition or the description of each term, this is the time change of the variable phi, right, within my control volume. It's equal to the flux of phi. Remember, this is the flux of phi transported through the surface of that control volume. And this will give me the flux of phi, and this is transported through the surface by bulk fluid motion, right? Keeping that in mind, this is convection term. This is the flux of phi transported by diffusion through still the faces or the surface of the control volume. And this is the change of the value of phi due to source within the control volume. So this is the interpretation of each one of these terms. So the time change for what's happening inside the control volume is end up to be a function of what's happening at the outer face, transport of that phi by convection, bulk fluid going through the faces, or by diffusion through the faces, plus what's happening internally due to an internal source. In a simple language, very, very rough simplification here, you guys recall the energy balance equation? This is simply E dot stored. This is simply E dot out. This is E dot in. This is E dot generated. That's in very simple language here, okay? So the time change of the energy stored is related to the energy leaving that phase by convection, whatever is coming in by conduction or by diffusion. But we combine the in and out, convection by itself and diffusion by itself. and this is the energy generated term. Again, this is just a very simple interpretation for that equation here. If we are solving steady state, the transient term will go away, right? This will go away. But if we are solving transient, this will be a different topic to talk about later on. But let's work for the steady state condition for now. So we will end up having the integral over the surface area for rho v phi dot n dA is equal to the integration over the surface area of kappa nabla phi dot n dA plus the integral over the control volume of S phi dV. So I would like to simplify that term a little bit. So we will do the following. We will assume the integration over the control volume of that source term dV will comes into an average value per unit volume multiplied by the volume of the control volume. So S phi average is an average source per unit volume multiplied by V, which is the volume of the control volume. Do you want to get a sensation with an example? If we're talking about a heat source, so I can present the control volume integral of the heat source dV by Q dot times V. This is the average source per unit volume. That's watt per meter cube, and multiplied by the volume of the control volume, which is meter cube. This is just an example here. And remember, if you get that per unit mass, right, or let's stick to it like this. So that's Q dot, the volumetric heat generation times the volume. This is the simplest way to deal with the source term, to average that into a value. And usually you would be given the average value. Could be a constant, could be a function, but this is always given an average because it's hard to integrate that term. So we end up having these two terms here, and these two terms is simply integration of certain quantity over the normal to the phase over the area of that control volume, right? And that's the same way here. So how are we going to deal with the control volume method? So again, we have a control volume. Let me get a lighter color pen. Let's assume this is my control volume here. Again, finite volume method does not deal with the information except at the center of the cell. So we will have a point P located at the center of the cell, okay? If I assume this is my X direction, this is my Z direction, this is my Y direction, okay? So I'm going to have a neighboring cell centers. I'm not going to draw the element here. This is just the center point of the cell in the right side of it. I'm going to call that the east cell center. This is the west cell center. I'm going to have one at the top. I'm going to have one down there. I'm going to call that the north. I'm going to call that the south. And you realize that cell center points are always capital, right? It's east, west, north, south, and the present cell that I'm interested in, okay? Then we call that the east face. This is the west face. This is the north face. And this is the south face. and we give that letter E small, W small, N small, S small. So small letters always refer to the faces. So faces, we have E, W, N, and S, all small letters. Integrating the general transport equation will give us the values at the center point, but on the faces, no information is known. I don't know any data on the faces, okay? So there is no value known on the faces of that cell here. Okay, then based on that, we can really approximate this equation to convert it into, remember, we still need to convert that equation into system of linear equation, okay? So in the simplest fashion, we will approximate how phi will it change within that control volume, and based on that, how phi change, we're gonna be able to calculate these integral terms and convert them into algebraic terms as well. Keep in mind, this is a general equation for a steady state, right? So keep that in mind as well. And remember, when we talk about finite volume method that addressing diffusion only, if I want to use a finite volume method to solve a conduction problem, this means that the velocity vector is going to equal 0 and the convection term will goes away, right? If you do finite volume method to solve convection, if the diffusion is neglected, remember that the kappa term will be 0, right? So that term goes away. So what I'm saying here, if you are solving only diffusion problem, this term will goes away because there is a velocity vector and the motion is not considered here. Assume I'm solving a two-dimensional conduction problem in a solid bar. So there's no velocity vector here. This term goes away. So it's going to be only the diffusion and the heat source, conduction and heat generation. If you're solving convection problem like fluid flow problem and the diffusion is neglected, kappa will be 0 to eliminate that diffusion term. You're going to end up having that convection term and depend on the problem statement if there is a source or not.